All right. Thank you very much, Anne. Good morning, everyone. First, I want to also thank the organizers for inviting me to give this tutorial on what I consider an extremely exciting, rapidly developing area of quantum pseudorandomness. And in particular, I want to talk about constructions, applications, and open problems regarding pseudorandom quantum states. Okay. And we have a lot of time during this tutorial, so in the tutorial spirit, please feel free to ask questions during the talk if any questions may arise. Okay, so since this is the very first talk in the very first day of QCrypt, and maybe not everyone has heard of quantum pseudorandom states, I want to situate where this topic lives in the broader context of quantum cryptography. So at a high level, one can divide quantum cryptography into three categories. The first one is called post-quantum crypto. And this is about designing classical crypto primitives to be secure against quantum adversaries. Okay. The second category is what I'll call information theoretic fully quantum crypto. The fully part is what I use to refer to the fact that even the honest users are required to have quantum computers, right? Maybe as part of the protocol, they have to generate quantum states and send them back to each other between the different parties over a quantum network. So not only the adversaries have quantum computers, okay? And QKD is, of course, a flagship example of this. In this third category, it's, again, fully quantum crypto. But now we'll make computational assumptions about the adversary. I should mention for the middle column, the information theoretic qualifier means that we make no computational assumptions about the adversary. They can have unlimited computational power, but the protocol should stay secure, right? That's sort of the appealing aspect or feature of things like QKD. But in this last category, we're going to then additionally impose computational constraints on the adversary. We're going to assume that they can only perform polynomial time computations, and using that assumption, you want to leverage it to obtain more powerful forms of crypto. So examples of this third category include primitives like quantum money, quantum copy protection, and pseudorandom states, pseudorandom unitaries falls within this category. Okay, so what are pseudorandom quantum states? At a high level, they are quantum states that can be efficiently computed, efficiently generated. But to an outside observer, they look random. These were introduced not too long ago by Ji, Liu, and Song. And since then, especially in the last few years, there's been a lot of interest in them. They were mainly motivated initially by quantum cryptography. So it turns out that you can use pseudorandom states as a basic building block to build interesting crypto primitives. But since there's also been applications to things like quantum machine learning, quantum complexity theory, mainly as a way of proving hardness of different quantum computational tasks. And recently, there's also been implications to the study of black holes in quantum gravity, which has been quite interesting. So pseudorandom states look to be very useful and just very interesting, fascinating objects in their own right. And there's also many things we don't know about them. So that's what I want to survey today. So in this tutorial, I'm going to cover first the definition of pseudorandom states, or PRS. Then I'll talk about constructions of them. How do you build pseudorandom states? Talk about some of their properties. Discuss some applications, canonical applications of PRS. And I'm going to focus on the cryptographic applications of them, because that's the subject of this conference. And then finally, I'll end with some open questions. Okay. All right, so let's start with the definition. So I'll explain pseudorandom states as a quantum analog of something called pseudorandom generators, which is an object that comes from classical cryptography. So just to draw the analogy, a pseudorandom generator is a deterministic polynomial time computable function, G, and it takes as input a lambda bit seed and produces an n bit output. Okay, so it takes in a classical bit string as input, outputs another bit string. And the output bit string has the property that no polynomial time algorithm, called a distinguisher, can distinguish the output of G from n uniformly random bits. Okay, so here n is assumed to be larger than lambda. So clearly, information theoretically, the output of this generator cannot be uniformly random. This is because G is a deterministic function. But nonetheless, the assumption or the security assumption of this PRG is that, if you're limited in your computational resources, you cannot distinguish the output from uniformly random. Okay. All right, so now what about PRS? So a pseudorandom state generator is going to have a very similar looking syntax. So now we have a generator G. This time it's a quantum algorithm, still runs in polynomial time. It takes in a lambda bit classical seed, but now it outputs an n qubit state. And the security assumption or security guarantee of this pseudorandom state generator is that no polynomial time distinguisher can tell the difference between copies of the output of this generator versus copies of an n qubit state sampled from the Haar distribution. Okay. So the Haar distribution is now supposed to be the quantum analog of the uniform distribution over bit strings. Just a quick refresher about what the Haar distribution is. So we all know that n qubit pure states are represented by unit vectors in a 2 to the n dimensional complex Hilbert space. And we think of this Haar distribution as really the uniform distribution over all these states. So in my head, I visualize the space of states as some kind of high dimensional sphere. And a Haar random state is just going to be a Haar random point on this sphere. Okay. A couple differences though between the uniform distribution over n bit strings and the Haar distribution over n qubit states. So first, one can sample efficiently an n bit string. You just sample the first bit and then independently the second bit and so on. You do that n times, you have a uniform distribution. On the other hand, you can prove that there is no efficient process that can sample a Haar random n qubit state. And that's because a Haar random n qubit state in some sense has exponentially more randomness than a random string. Okay, so the defining feature of the Haar distribution is that it's unitarily invariant. So if I plucked a state psi from the Haar distribution, multiplying the state psi by any fixed unitary u is going to give me another state that its distribution is also Haar random. So we say that this distribution is unitarily invariant. All right. Okay, so now with this we can more precisely give the definition of a pseudorandom state generator. So we say this quantum polynomial time algorithm G is a PRS generator if given key k, which is lambda bits long. G of k outputs an n qubit state that I'll call psi sub k. And for all t is going to represent the number of copies of the state that we want to distinguish. For all time polynomial in the security parameter lambda, for all polytime algorithms D, giving D t copies of psi sub k, where k is sampled uniformly at random, the output of the D is the same, or approximately the same, as giving D t copies of a Haar random state. Okay. So D outputs, let's just think of it as outputting a yes or no answer, okay, a single bit. And the probability of that bit being 1 is going to look very close in both cases. Right? You may wonder, what is the role of this parameter t, the number of copies? And as we all know, quantum states cannot be copied. This is the no cloning theorem. So it really makes a difference in general whether you give an algorithm t copies of state or t plus 1 copies of a state. Yeah. Oh, hey.
So for the benefit of the recording, we'll use the microphone for the questions.
Thanks. Is it relevant that t is constant here and is not, for instance, be allowed to be polynomial in lambda?
Oh, good. So yeah, I guess I wasn't so precise here, but t is allowed to be a function that grows with lambda. You can ask whether it has to be polynomial in lambda or not. Here, the fact that we're restricting d to be a poly lambda time algorithm says t can be at most polynomial.
Thanks. Yeah.
Yeah. Thanks for the question. Yeah. So think of t here. T can even be a growing quantity that's any polynomial in lambda. Okay. Great. Yeah. Any other questions about the definition of a PRS generator? All right, so yeah, going back to the number of copies, this is saying that, right, so in general, it could be the case that if you have two ensembles of quantum states, giving one copy of each, it cannot be distinguished by, say, a class of adversaries. But maybe if you gave two copies of each, suddenly the fact that you have two gives you extra power, and now you can distinguish. This definition of PRS generator says that no matter how many copies you give, as long as it's at most a polynomial number of copies, you cannot distinguish this from the Haar distribution. Of course, if you gave an exponential number of copies of the state, then one could perform, say, tomography and learn an exact classical description of the state psi sub k, in which case then you can actually hope to distinguish. But this is saying, if you're far away from this exponential copy regime, you have pseudorandomness. Okay, so another feature here is you might have heard of, if you're not familiar with pseudorandom quantum states, but you might have seen something called T-designs. So the definition of T-designs looks very similar in some ways, but it's also it's actually very different. So in T-designs, the order of quantification is flipped. So it says if you fix a number of copies t, then t copies of psi sub k cannot be distinguished from the Haar distribution by not only polynomial time algorithms but any algorithms, right? So it's actually an information theoretic object, and it's known how to construct these and so on. But the thing about T-designs is once you give more than t copies of a T-design, then in principle, one could distinguish it in polynomial time. Okay. But here, this is saying, for any t that's polynomial, there's just no polynomial time distinguisher, right? So that's an important distinction. Okay, so that's the definition. Let's move on to some constructions. How do you build pseudorandom state generators? So here's a canonical construction that's quite simple to describe. It's very nice. So here's how you can build pseudorandom states from pseudorandom functions. So let this family f sub k, which maps n bits to 0, 1, it's indexed by keys. Let this be a post-quantum pseudorandom function family, a PRF family. What does that mean? So this means that for all polynomial time distinguishers D, giving D query access to a randomly selected function f sub k, right? So k is not known to the distinguisher. All it gets is just black box access to one of these f sub k's. D cannot tell the difference between f sub k and query access to a truly random function. Okay. And it's known that post-quantum PRFs exist if and only if post-quantum one-way functions exist. Right? So Zandri proved back in 2012 that the classic GGM construction is secure against quantum adversaries. Okay, so let's assume we have one of these. So Ji, Liu, and Song proposed what we call the binary phase PRS. So the pseudorandom states psi sub k are defined as follows. It's going to be the uniform superposition over all n qubit basis states, x. But each basis state x has a plus or minus one phase that depends on the value of the pseudorandom function, the PRF f. That depends on, and the way you select f, it depends on the key of the PRS. So the PRS gets the key k, it's just going to then choose the corresponding PRF and use that for the phases in this state. Okay, so this is clearly efficiently computable in polynomial time, right? Because really all you're doing is just computing a PRF, which by assumption is efficiently computable. How do you know that this state is pseudorandom, right? We have to argue that this state looks indistinguishable from a Haar-random state. So I'll just briefly sketch, how you begin to analyze this. So let's say we have t copies of the pseudorandom state psi sub k, right? Psi k tensor t. So the first thing you argue is that using the pseudorandomness of the underlying PRF family, this t copies of this state is computationally indistinguishable from the following complicated looking superposition. It's a superposition over all bits, it's over t bit strings each of length n, x1 up to xt. And the phases corresponding to each of these xi's are now, instead of being pseudorandom, are just going to be uniformly random plus or minus one values. Okay. So the fact that these two states are computationally indistinguishable, this just follows directly from the security of the PRF. Right? But now these alphas are just truly random. Now they're not pseudo-random. Right? And then what you do is you say, well, let's now look at this state and look at the density matrix corresponding to this, where you average over all alphas. Okay? So imagine taking this state and then writing the Hermitian conjugate and then taking the expectation over these alphas, right? And just doing a little bit of calculation, it's not too complicated. You can actually show that this density matrix looks like the density matrix that you would get from t copies of a Haar-random state, which one of the basic facts about Haar-random states is this density matrix is proportional to the projector on the symmetric subspace. So I won't go through the calculations here, but it's not too hard. So let me just leave it at that. Any questions about this construction or the analysis? All right, so this is sort of this is a nice, easy construction to remember. All you need to get security is to just assume the existence of post-quantum one-way functions. It's a pretty mild assumption. What if you didn't want to assume the existence of one-way functions? Okay. Is there another construction that might be plausibly considered a pseudorandom state generator? So here's another one, which we know how to argue is secure under any well-known or well-understood assumption, but nonetheless is plausible. So let me describe this. So here the generator is going to take the key k, and it's going to interpret it as a description of a quantum circuit, right? So k, it's just a sequence of bits, and imagine these bits just describes, your favorite quantum circuit with 2 qubit gates. So, picking a uniformly random K is going to give you a uniformly random quantum circuit under some natural encoding of circuits. When the generator gets this circuit description, it's just going to run the circuit on the all zero state and output the resulting quantum state, right? So this is what the size of K is. All right. So really, these pseudorandom states are just outputs of random circuits. And random circuits have been studied a lot in the last few years, especially because of these quantum supremacy experiments and also interests in studying black holes as information scrambling objects. So, a lot of people, for different reasons, conjecture that random quantum circuits, at least in a very intuitive sense, they're pretty chaotic, they're structureless, hard to predict. So based on this, it's reasonable to conjecture that it gives rise to pseudorandom states. So I think this is a very interesting conjecture, and it'd be really nice, and I think this is one of the big open questions or directions in this area, is to try to give evidence or more quantitative understanding of when the outputs of random circuits give rise to pseudorandom states, right? Can you show that in order to be pseudorandom, the circuit has to be a certain depth? And I think there's been some really interesting work lately by some folks at UT Austin showing that, for example, these random circuits have to have at least some number of T gates, right? So that's some initial steps towards this direction. But let me point out that this qualitatively seems like a very different construction than the binary phase PRS. There's no one-way functions here, right? You couldn't find one if you tried. So it looks pretty different. Okay, so let's talk about some properties of pseudorandom states. So the first basic thing to recognize is that pseudorandom states, they're a computational object, right? Like they cannot exist unconditionally. We have to, if we're going to use them, at least today, we have to make assumptions about their security. And the reason for this is because if you make no assumptions on the adversary or the distinguisher, given exponential time, it is possible to distinguish between pseudorandom states and the Haar distribution. Right? So why is that? So you can do this just by a dimension counting argument. So let's look at the output space of a pseudorandom state generator, right? What is the dimension? So the span of psi sub k raised to tensor t, no matter what t is, the span of this output space has dimension at most 2 to the lambda. That's because there are at most 2 to the lambda different output states, right? So in some sense, the output space is sort of fixed for all t. On the other hand, if you look at the span of the set of t copies of all possible quantum states, this has dimension, this binomial coefficient, 2 to the n plus t minus 1, choose t. So if you choose your parameters correctly, for sufficiently large t, that's some polynomial in n and lambda, the dimension of the output space of, say, a Haar random generator is going to quickly exceed 2 to the lambda, the dimension of the output space of the PRS. So all you have to do is just measure the projection onto the output space of the pseudorandom state generator, and you can distinguish between Haar random states and the PRS with high probability, right? Because the dimensions of both are just so different that the output space of the generator is going to look like a tiny sliver in comparison. Okay, so you can do this in exponential time, and the assumption of the PRS is you really need that much time essentially to do this distinguishing, but you do need some computational assumptions. All right, so let's do some comparisons between PRS and PRG, pseudorandom generators. Right? There were supposed to be analogs of, PRS is supposed to be analogs of PRG, so let's just see how far this analogy extends. So with pseudorandom generators, they're extremely useful in classical cryptography and just classical computing in general. With pseudorandom state generators, when you look at the definition, it's not immediately obvious how to use this for cryptographic application. Okay. We'll see how you can actually use it for crypto, but it takes some thought. It took, it wasn't like the first paper that introduced PRS, it kind of had some sort of crypto applications, but it wasn't super, super clear. Okay. A nice thing about pseudorandom generators is that they're equivalent to one-way functions that you can efficiently compute one way, but it's hard to invert. Okay. So this is a really nice fact about pseudorandom generators and one-way functions. Like these things all turn out to be equivalent. What about pseudorandom state generators? As I mentioned, they, okay, that's weird. Okay, well, let's just turn to the side. Pseudorandom states don't generically imply one-way functions, right? Like I said, there's this candidate constructions involving random circuits, but there's not apparently any one-way function inside. And in fact, there's some formal separations, due to Kretschmer and others, showing that in a black box way, if I gave you an arbitrary pseudorandom state generator, it doesn't necessarily have to imply one-way functions. Okay, so another nice thing about pseudorandom generators is that if you can stretch just lambda bits of seed to have one extra bit of pseudorandomness, right, where the output length is lambda plus 1, this is enough to bootstrap it to generate any amount of pseudorandomness that you want, right? You can, just iterate this pseudorandom generator and get as many random bits as you like. This is a super nice feature. But it's not clear this works for PRS, right? So if I handed you a PRS generator, it takes in lambda bits and produces a lambda plus 1 bit quantum state as output. And I said, well, actually, what I wanted is a lambda plus 2 pseudorandom state, lambda plus 2 qubit pseudorandom state. As far as we can tell, there's not a way to get this, right? You're sort of stuck with what you got. Even worse, here's kind of even a trivial thing about PRGs that takes no thought. If I give you an n-bit pseudorandom bit string, and I chop it in half, those half bits are still going to be pseudorandom, right? But that's not the case with PRS, right? If I give you one of these psi sub k's that's on n qubits, and I just give you the first n over 2 qubits, first of all, this thing is going to be a mixed state, right? Because pseudorandom states are highly entangled. So if you, just chop it in half, you're going to get a highly mixed state. And this thing can be easily distinguished from, copies of the Haar random state. So even just truncating PRS is, you're not supposed to do that, right? And this is, you also can't copy outputs of PRS, right? Just because quantum states are not generically clonable. So for all this reasons, there's a lot of differences between pseudorandom generators and pseudorandom states. And really the feeling you get is that pseudorandom states are quite brittle, right? They don't have the same flexibility and malleability in the sense that pseudorandom generators have, okay? Which makes, because of these reasons, it makes it a little harder to use. Okay. So now let me turn to the application section. Let's see how we can use, despite all these reasons, we can actually find useful applications of PRS. All right, so what were the applications of PRGs? And I mentioned that PRGs are equivalent to one-way functions, but sort of like a famous result in classical crypto is that they're equivalent to many other things. And so first of all, PRGs are equivalent to one-way functions, which are equivalent to PRFs, which we already saw. And it's a nice equivalence between these classical pseudorandom objects. But they also turn out to be equivalent to what are called mini-crypt primitives. So these are, you can sort of think of it as capturing the class of, symmetric key cryptographic functionalities, like things like private key encryption, commitments, digital signatures, zero-knowledge proofs. So if you have, any one of these objects, you can construct these really cool schemes, and vice versa. If you have any of these, no matter how these schemes were constructed, you can reverse engineer it and construct either, say, a one-way function or a pseudorandom generator, so on. Okay. So all of these things are there's this nice equivalence between it. It's a very nice picture, right? But I should point out that these equivalents only hold in the classical world. But what happens when, say, the parties and the protocol itself uses quantum resources or uses quantum communication? And then it's not so clear what equivalences hold and so forth. So the major question is, what cryptographic primitives can you build directly from PRS? So here's what the map that's starting to emerge. So from PRS, you can directly build quantum commitment schemes. You can build digital signatures that work to sign, security holds if you sign a message once. There's a nice implication, like once you have quantum commitments, then another result, which is known a few years ago, you can use this as a black box to construct protocols for secure multi-party computation, which is quite cool. I mean, these protocols are highly interactive, but all they need is just some commitments. Okay. All right, but what about other primitives? And it's not clear how to use PRS to construct anything else directly. So what one can introduce is a slight relaxation of the notion of PRS. And this is what I'll call PRFS. Okay, so kind of a mouthful, but what it stands for is a pseudorandom function-like states. Okay, so this will turn out to be the quantum analog of pseudorandom functions, and I'll get into the formal definition later. But once you introduce this relaxation, then it becomes much easier to see how you can construct other quantum crypto primitives. You can obtain things like pseudo one-time pads, message authentication codes, symmetric key encryption, and some other things. And what's the connection between PRS and PRFS? Currently, we know how to construct this more flexible object from PRS in a certain parameter range. Okay. And in this certain parameter range, it's enough to get pseudo one-time pads, so that's cool. What we don't yet know is, in that parameter range, how to get message authentication codes or other types of symmetric key encryption. So that's an open question. But we're starting to fill out these branches and see that from PRS or PRS-like objects, we can obtain interesting crypto primitives. Okay. And I'd like to point out that all of these arrows don't require one-way functions, right? Really, all that's needed is you give me a PRS or a PRFS as a black box. I don't care how you constructed it. Maybe it's one of these random circuit constructions, who knows? And from that black box, I can build protocols for all of these functionalities. So let's see how, for example, you can build commitments from PRS. So let me just do a quick reminder of what a commitment scheme is. I think this is very basic to this audience, but just for completeness. So a commitment scheme, it's a protocol that's executed between two mistrustful parties, committer and a receiver, and it's the cryptographic equivalent of putting a message in a sealed envelope that's revealed later. So the first phase of this commitment scheme is a commitment phase. So the committer gets some message M, and they have some interaction with the receiver. They talk back and forth, and at the end of the commitment phase, the receiver is going to have a piece of data called the commitment, and it's this sealed envelope, right? So this receiver has no idea what the message M the committer committed to, and this is called the hiding property of the commitment scheme. Okay? So this piece of data does not tell the receiver what M is. Sometime later, the committer will decide to reveal, to open the commitment, and which they'll interact, and then the envelope basically gets opened, and then the receiver will get this message M, and the receiver can check whether the committer was honest. Basically, the committer cannot open to a different message M prime that was different from the original message that was committed to. So this is called the binding property of a commitment scheme. You can imagine that something like this would be really useful in like an auction where you put your bids in a sealed envelope and then later your bids are revealed, for example. It's a very basic primitive that's used as a building block in many, many different types of crypto primitives. So it's nice to think about. So here's a very nice construction of quantum commitments from PRS. And in fact, this commitment scheme is actually non-interactive, right? It does not require back and forth communication between the committer and receiver. There's only one-way communication from the committer to the receiver. So here's how it works. So so first assume that you have a PRS, psi sub k. And we're going to also assume that it has a big enough output length. So, lambda is the length of the key. But we're going to assume that the number of output qubits is at least 3 lambda. Okay. This is not without loss of generality because like I said, we don't know how to generically stretch the outputs of PRS. That's a very interesting open question. So let's just assume that we have a sufficiently large PRS. Now, to commit to a given bit B, so now the message is only 1 bit, the committer is going to generate this state. Okay, so so this state I'll call phi sub B. It's going to be the uniform superposition over all keys of this PRS K, and over all one-time pads X and Z. And conditioned on K, X, and Z, it's going to generate a copy, just one copy of the pseudorandom state psi sub k, right, which it can do efficiently. And then depending on the bit B, which is trying to commit to, it either applies a quantum one-time pad P or not. So if the bit B is 0, then there is no one-time pad applied. If the bit B is 1, then you apply the corresponding X's and Z's. Okay. So there's 2 parts to the state. There's these K, X, and Z, and then there's this pseudorandom part. To commit to, in the commitment phase, the committer is just going to generate the state and then send this second part of the state, the C register, to the receiver. This is the commitment. So the receiver is going to have this part. And once the committer decides it wants to reveal, it's just going to send over the remaining registers. So it's going to send over the R part, right? So how does the receiver check? Well, it has the whole state, so it can just uncompute. It can just try to invert the circuit for generating psi 0 or psi 1 and check which state it got. All right, so why does this work? Well, first, the receiver can actually verify the commitment because these 2 states, psi 0 and psi 1, are almost orthogonal. So this uses, this is not, doesn't use any pseudorandomness. This just uses the one design property of the one-time pad, right? So, once you one-time pad, this part, these two states, psi 0, phi 1, phi 1, phi 0, are going to be almost orthogonal. Okay. So the receiver can indeed verify the commitment. All right, what about the computational hiding? So the hiding property is going to be the thing that depends on the pseudorandomness. So in fact, the hiding holds computationally, not information theoretically. The receiver cannot efficiently distinguish between whether it got B equals 0 or B equals 1 when it only holds the commitment. Okay. And the way you show this is, if it could, then it could efficiently distinguish between the maximally mixed state, okay, which is the density matrix that it would see in the B equals 1 case, right, because of the one-time pad, versus just the uniform mixture of all the pseudorandom states, right? So these two density matrices are going to be actually, statistically far, but because of pseudorandomness, they cannot be distinguished, right? That's where the hiding property comes from. Okay, what about the binding property? You want to argue that the committer cannot change his mind about which bit he wants to reveal after he sent off the commitment, right? So after he sent off this register, all he's left with is this part of the state, this R part. And you want to argue that there's no quantum operation that you can perform to change the global state from phi 0 to phi 1. And this holds information theoretically. This is statistical. Like once he sends off this part, there's nothing he can do, give it exponential time or otherwise to change his mind. And that's because the reduced density matrices of the C part are, like I said, they're far apart. So there's no way he can change the state, the global state from phi 0 to phi 1 only by acting on R. So this is the Murame-Yamakawa construction of quantum commitments using only PRS. And you can see that this used the PRS in just a black box way. Any questions about this construction or how it's analyzed? Yeah.
It's a simple question, just my lack of understanding. What's the difference between X and Z, or why do you have both an X and a Z? It doesn't seem like you independently did anything with either of them.
Okay, good question. Yeah, so I guess in some sense it was redundant based on this description. So the quantum one-time pad, you apply random X operators and random poly Z operators. And the choice of which X operators, which qubits you apply X and Z. Yeah, but here it's a little redundant. I agree. Yeah, thanks for the question. Any other questions? Okay, so that's the first. I think it's a very nice application. Now I'm going to turn to an example of an application where it's not quite clear how to use PRS. So that's why we need to introduce this thing I call PRFS, pseudo-random function-like states. So what's different about these? So it's defined in a way to make life a little, as a protocol designer, easier. So here you have, again, a generator. It takes in not just a key, but also a D bit, just call it input for lack of a better name. This is the input X, okay? And one way to sort of distinguish between these two things that go into the box is the key K is supposed to be hidden from the adversary, but this input X is allowed to be public. That's okay. Now, for every pair K and X, there's a different state that's output. Yeah, I'll say what the pseudorandomness property is in the next slide. And it's supposed to be the quantum analog of a PRF from classical cryptography. So that's why we call it function-like. All right, so what's the pseudorandomness of a PRFS? So given a key and an input x, so g of k comma x will output this state psi kx. And now, this look a little more complicated. So, for all copies t, for all distinct inputs x1 up to xs, all right? And for all distinguishers d, and here's the thing, d can know what inputs x1 up to xs we're talking about. This distinguisher d is going to get, t copies of pseudorandom state psi 1 up to psi s. How are these generated? Well, you picked a random key k that's hidden from the distinguisher d, and the psi I is just going to be g of k comma xi. Okay. Right, so you have all these inputs x1 up to xs, these points, and you evaluate g on these points as well as this hidden key. And you give the outputs all, and t copies thereof, all to the distinguisher. And it's just going to look like to the distinguisher, it got, t copies of s independently chosen Haar random states. Right, and like I said, it's important that the distinguisher is allowed to depend on x1 up to xs. This is not hidden information. So that's what a PRFS generator is. What do we know about it? Well, it's not hard to see that this is a strict generalization of a PRS generator, right? If you have PRFS, then you clearly have a PRS generator just by fixing this input x to, say, the all zero string, right? But in fact, you can vary x and get different pseudorandom states. How can we construct it? Well, you can use something similar to the binary phase construction and easily argue that it's a PRFS. But let's say I don't want to assume the use of one-way functions, right? What if someone gave me a PRS as a black box? Not a PRFS, but just a plain vanilla PRS. Can I use it to build one of these more complicated objects? It's not clear, at least not in all parameter regimes. So this is an open question. You might wonder whether, this famous Goldreich, Goldwasser, Macaulay construction, GGM, it's a classical recipe for taking a PRG and building a PRF. So you might say, well, PRS is like a quantum PRG, PRFS is like a quantum PRF, so why don't I just try to replicate this recipe? Well, the thing is, as with many classical security reductions, they do all sorts of non-quantum friendly things like copying outputs, right? This is a no-no. You can't copy the outputs of a PRS. So, this seems incompatible with PRS. So, we don't have a quantum GGM for lifting PRS to PRFS. All right, so like I said, this is an open question, but here's what we can do. In this parameter regime where the input length, right, this x part, the number of bits is O of log lambda. Okay, so it's kind of short, but still something. So if you have the existence of PRS generators with n plus d qubit outputs, then you can sort of split it and get a PRFS generator with d bit inputs and n qubit outputs. So here's just the basic idea. So you're given this PRS generator with n plus d qubit outputs, right? So for each psi sub k, I can write it as a superposition where the first d qubits interpreted in the standard basis is some x, and then you have some residual state which depends on the key k as well as x. So if you can generate this state, then by post-selecting on specific x and outputting the residual state, you can get this psi sub kx. That's your PRFS generator. And the reason this post-selection is actually doable efficiently is because the length of x is not too large. It's only log lambda bits. So by trying enough times, in polynomial time, you can actually obtain this residual state. And you can argue that this residual state all look random, at least to a polynomial time distinguisher. Okay. So, this only works in a particular parameter regime, but it's enough to get some interesting applications, which I'll describe next. Okay, so let's see how we can get a form of private key encryption from PRFS. Right. So I'll discuss the pseudo one-time pad. And it goes, I shouldn't even have to say this, but yeah, Shannon showed that the one-time pad achieves perfect secrecy, but of course the issue is that it requires a random key as long as the message. The pseudo one-time pad is the same thing, except you use a pseudo-random string instead of a completely random string. So you can save on the randomness. Can we build pseudo one-time pads from pseudorandom states? It's not quite obvious how to do this, but let's use PRFS as a building block. So let's say we want to encrypt R bit messages. So M is R bits. And let's assume that someone has given us a PRFS generator where the X part has length O of log R. So what do we do in order to send message like this message M to our friend? So you and your friend share a secret random key K. You're going to generate R pure states, psi 1 up to psi R, that will depend on your message. And here's how the encoding works. So psi I is going to be the encoding of the ith bit of your message. And you're just going to take your generator, plug in the secret key, and then you're going to, for the input part, you're going to concatenate the index of the bit that you're sending with the ith bit of your message. So this is, log R bits to specify which index, and then there's an additional bit specifying the MI. You're going to get some pure state psi I out, and that's what you send off as the representing the ith bit. Okay, so now the receiver gets these sequence of pure states, and to decode what the ith bit is, it has a secret key, so it could just test if it's equal to G, K, comma I concatenated with 0. If so, then the ith bit of the message is 0, otherwise it's 1. Right, that's it. Okay, so it takes a bit to analyze this and show that all of this works. And in particular, just even testing this testing procedure to argue that this works, you need to use a pseudo-randomness of G. But you do the analysis, and from the point of any polynomial time adversary, all of these states look completely random, independent of the message that was being encoded. Okay, so here's the theorem. Assume the existence of PRFS generators with log R bit inputs, and the output length, like the number of qubits that the generator has to output, has to be asymptotically larger than log R, mild assumption. Then there exists secure quantum pseudo one-time pad encryption schemes for R bit messages. Okay, so that this is an illustration of how we use PRFS to get some private key encryption schemes. Thanks. All right, so let me just quickly summarize some other interesting applications of PRS, really to just show you, why people think PRS is interesting, other than for the crypto applications just mentioned. So in terms of quantum complexity theory, PRS can be used not to obtain protocols, but to show hardness of some fundamental quantum information theory tasks, like compression of quantum states. So it's a very nice vehicle or tool to show hardness results. I had also alluded to this. It's also very interesting from a foundations of crypto point of view that PRS does not imply one-way functions in a black box way. So this is, Kretschmer, who will speak later today about this. He, first gave evidence that, there's a separation. And so that's very intriguing because it looks, it's sort of gospel in classical complexity and classical crypto that one-way functions are really the minimal assumption needed for any interesting crypto. But in the quantum world, things look a little different. And so it's an exciting time to try to figure out how exactly this landscape looks. In addition to the very basic applications I mentioned before, now there's more uses of pseudorandom states, like pseudorandom proofs of destruction. I think Amit will give a talk about this later today, so be sure to attend this talk. You can obtain quantum public key encryption, non-interactive public key encryption using pseudorandom states. So that's been an exciting development. I mentioned applications to quantum machine learning. So it's also PRS can be used to show the hardness of learning quantum processes in quantum states. In this world of quantum gravity, so people like to, I guess, in the physics world, people are very interested in thinking about this black hole information paradox. And what they've come to these days is they find it a very attractive thing to think of black holes as a pseudorandom quantum object, and really the state of the global pure state of a black hole and its radiation maybe can be regarded as pseudorandom in ways. And think of it in this way has apparently given them insight. Also, there are PRS has been used to come up with this notion of pseudo entanglement. So these are states that have low amounts of entanglement, but to any outside observer actually have high amounts of entanglement. And apparently that has implications for this complexity of the ADS-CFT correspondence, again, from this world of quantum gravity. And just more broadly, coming up with the notion of quantum pseudorandom states has led people to think, well, what other quantum pseudorandom objects are there out there, right? And what can we do with them? And also, again, really in the last year or two, there's just a flurry of activity where people have come up, with objects like EFI pairs, one-way state generators, pseudorandom unitaries, and these are all different objects with very interesting properties, and it's very unclear how all of them relate to each other, and that's sort of an exciting avenue of research. Okay, so let me wrap up by just showing a few open questions. I mentioned a bunch throughout the talk, but let me consolidate some of them here. Sort of a very nice direction is to figure out what else can we build from BRS in a black box way. Can you build PRFS? One of my favorite questions is whether you can build digital signatures that can sign many messages in a black box way from PRS. And this would, I had mentioned earlier that one-way functions is equivalent to, and PRGs are equivalent to all these mini-crypt primitives. And we can essentially replicate that picture with PRS, except there's this one annoying omission, which is we don't know how to get digital signatures. And we don't know if this is inherent or we just haven't come up with the right protocol yet. So I really like that. Also there's, symmetric key encryption, encrypt many messages. Okay, what about the relationship between PRS and other quantum cryptographic functionalities or primitives that we know of out there, like quantum money? Can we show that you can use PRS to build a public key quantum money scheme? I mean, that would be amazing. Or if you cannot, can you give it evidence that you cannot? Maybe in the form of an oracle separation or something like that. What are other candidate constructions of PRS, right? So I gave two. There's the one-way function-based one, or the PRF-based one. There's a random circuit one, are there other ones that are plausible or interesting, and can we give evidence for their security? And again, going back to this more broad, open question, or this area of this avenue of exploration, what are other interesting quantum pseudorandom primitives, and what are their properties and uses? So with that, thanks for listening. Happy to answer any questions.
Hello, I have a question. So when you talk about pseudo-random states, you mostly talk about pure states. So what happened to mixed state? Can you generalize it to mixed state so that you can have a better connection with like traditional pseudo-random state? Yeah, classical one.
Yeah, thanks for the question. So you're asking if, so here I've defined pseudorandom states as being pure. Is there a notion of pseudorandom mixed states? That's a very interesting question. I guess maybe one basic thing that comes to mind is I don't know, what would be the analog of the Haar distribution over mixed states? I'm not sure if there's a canonical choice or a good choice of Haar distribution over mixed states. I don't know, maybe someone has an idea. Is there an answer, or? Yeah, so I mean, so I don't know. It could be an interesting direction.
What about just maximally mixed state?
So the maximally mixed state, I mean, that's easy to produce, yes. So yeah, just without any computational assumptions. Yeah.
And I also think like from your talk, like there's like some inspiration from ADS-CFT, and I think maybe some of the construction there are for mixed states, right? Like because they are considering black holes, like thermal states. So I don't know.
It could be, yeah. I'm not too familiar with that line of research. So yeah.
So you mentioned at the beginning that Haar random states are difficult to generate. You cannot generate them efficiently. So how do you falsify the pseudo-random state assumption? How do you check that an adversary can cheat? Do you like fix T and then use T designs?
Yeah, that's a good question. So yeah, maybe, I don't know, maybe Gorion has a good answer to this, but I think maybe one way of thinking about it as a falsifiable assumption is, the adversary claims they can distinguish between, T copies of the PRS from T copies of the Haar random state. So once you fix that T, then you can use a T design and then compare.
Yeah, okay, thanks.
Thanks for the presentation. Very nice, very clear. There is one thing that keeps puzzling me, and that's if you take a pseudo-random state and you measure it, do you or don't you get a pseudo-random bit string then?
Good. So that's a good question. So it is true that if you take a pseudorandom state and you measure it with very high probability, you get something that looks like a uniform string. But I wouldn't consider it pseudorandom or useful because you can't get that same string again. There's no process to recover that string, right? So in the sense, it's easy to generate randomness, but for crypto applications, you want to have some deterministic way of getting that same random looking string again in a deterministic way. So that's what you can't do via this process.
Yes, I see. I had sort of a follow-up question, but I think I already see the answer to it. My question would have been, so why can't you use this then to stretch pseudo-random state by using this pseudo-random string as the seed? But then I see now you don't get a deterministic state then, of course.
Right, yeah.
Okay,
That's the
thanks.
challenge, yeah. Thanks for the question.
I was interested in why you were thinking about separating PRSs from quantum money.
So maybe this is because I'm really a complexity theorist at heart, and so I find it very interesting to understand what this landscape of all these quantum primitives look like, and what are the relations between them. Like, if you give me one thing, can I build another thing from it, and what are the reductions? And so in classical crypto, there's been a lot of work, and now I think we have a pretty good picture of, there's like some primitives that are like easy to get, like symmetric key crypto. All you need is a one-way function. But if you want to get something a little more high-powered, like public key encryption, this seems like it requires a lot more work. And in fact, now we have an explanation of why it's harder, because in fact, there's separations. And in studying these separations, we've learned a lot about the nature of these primitives, and we've just learned a lot. I think it's a very useful endeavor to try to map this out. And so similarly, we'd like to understand the structure of quantum crypto. Is quantum money inherently more difficult? I mean, it's a pretty difficult thing to try to construct, but do we have good reasons for it? And trying to get separations like this, I think, would help illuminate why it might be more difficult.
Sure, thanks.
In the spirit of tutorial talks, please feel free to ask any and all questions. This is your chance to query Henry. He didn't talk about oracles, but we could have talked about oracles here. Henry, your oracle, or oracle.
Oh,
So
my goodness.
please.
Hi, thanks for the talk. So just as a follow-up to the previous question about Haar-random mixture of, as in the Haar-random version of mixed states, why can't you just have just any density matrix and then you pick a unitary Haar-randomly in an IID fashion and then mix those? Wouldn't that work exactly like the pure state case?
So you're saying, how do you generate so what would be your starting mixed state?
It wouldn't matter, right? Because it would, like, you're just mixing it fully anyways. It's just like for the pure state case, it would not matter what your starting state would be, right?
Right. So one difference is that it matters what the eigenvalues of the starting mixed state would be. So what you're mixing would be the eigenbasis, but the eigenvalues would stay the same. And you wouldn't like necessarily explore the entire space of density matrices.
Right. Okay.
Yeah. So
thanks.
that's one. I mean, maybe you can fix an interesting sequence of eigenvalues, but I don't know like what would be. Yeah.
Thanks.
This side is doing much better in questions, by the way.
It's not a competition, but
I'm about to kill that streak, I'm afraid. As I've understood it, your techniques are all using classical generation of using, and then quantum generators that make the states, but it's all classical inputs. Is there anything to be gained by having a small amount of quantum inputs? Because I could imagine you would have, for example, distributed entanglement of, not a lot of some pairs, and then they'd be guaranteed to have, correlated quantum inputs to their independent pseudo, random state generators. So then they could generate equivalent states on the two sides. Does that help at all?
I absolutely love that question. I think it's very interesting. So yeah, so just to kind of repeat, so you notice in this definition, it takes the generator takes a classical input and produces a quantum state, right? And okay, you get a lot of interesting things out of it. But what if it took in some quantum input and did some pseudorandom something, and did what sort of new notions of pseudorandoms can you get? I have no idea. I think it's super interesting. I mean, one thing that I thought would be interesting to think about, but I haven't yet had the chance to think about what if you started with like a small Haar random seed, like you get in a small state that's like, 100 qubits, maybe you're promised that it's actually Haar random, like, some alien gave it to you. Can you use this as the seed for something much more interesting? I mean, I guess maybe you can think of it as related to the stretching question. Can you like stretch it into 1,000 qubit Haar random looking state? I don't know what would be a good process to do that, but yeah, so I think that anything along those lines is a very interesting direction to investigate.
Can I ask a quick question?
Please.
So in explaining the definition of this pseudorandom quantum state, there you make a distinction on the power of distinguisher, namely it should resist this distinguisher of any polynomial power instead of some low polynomial. Does that make this primitive easier or harder? Is there an example?
Yeah, so if I understand your question, you're asking if you change what computational power is given to the adversary, how does that change the security of the pseudorandom state generator?
Yeah.
Yeah, so there was a part in my talk where I mentioned that if you're given, say, exponential time, then in principle, by performing a measurement onto the output space of the PRS, you can actually distinguish between the two. And I think it's a part of the security assumption, right? You could assume the existence of a pseudorandom generator where if an adversary uses sub-exponential time, it still cannot distinguish. That's just depends on the strength of your, like how many bits of security does your PRS generator have? Yeah, so I would consider that as another parameter of the PRS.
Okay, thank you.
There's a question. Sorry.
Yeah. So I remember previously you showed that you cannot construct quantum money from collision resistant hash function. So I think collision resistant hash function imply one-way function. From one-way function you can construct PRS. So if you can construct quantum money from PRS, this means you can construct collision resistant. You can construct quantum money from collision resistant hash function. So.
Yeah, so good. So I think you're referencing there's some work earlier on separating exactly this question, separating quantum money from PRS. That's only a special type of quantum money where there's a severe restriction on the verifier. Like that only makes classical queries, so it's not a clean, full separation.
But at least for that type of quantum money, you can separate that from PRS.
I think so, based on your logic, yeah.
So I have a simple one. In the cases of your applications where you only have classical input, classical information input and output, like crypto or so on, is there anything that you really would gain by the detour of using the quantum states in between, instead of just, taking the classical primitives right away?
So you're asking, if you wanted to do crypto, like build a commitment scheme or encryption, why would you use PRS? I mean, I wouldn't. I think I think there will be applications where you genuinely, PRS seem really like the right tool for crypto. Currently, we don't. For quantum. Yeah, I guess I don't have any compelling applications off the head at the moment. It's sort of it. I would say it like this: like it wasn't even clear for several years whether you could use PRS for interesting crypto at all, and that's really been only apparent in the last couple of years. So I think hopefully in the next few years we'll see actual compelling use cases from the crypto point of view. I mean, from the complexity and quantum gravity stuff, it's already proven useful. Thanks.